Hi, everyone. This is Michael Lee. I'm the founder of the Data Incubator. We're a data science training and AI company. We're probably best known for our fellowship, which helps PhDs and master students enter the industry as data scientists. It's a completely free fellowship for the folks who get in, and you can apply online at thedataincubator.com. We also offer a number of online courses for working professionals, as well as corporate training. And if you're interested in either option, you can look at our website, dataincubator.com, as well. But today, we're going to be doing another installment of our regular monthly web series, Data Science in 30 Minutes. This is really a regular series about data and its role in the world. Previous speakers have included Kirk Bourne, who's the director of data science at Booz Allen Hamilton, Holden Corral, an engineer and a lead engineer at IBM and a core contributor to Apache Spark, Zubin Garmani, who's the chief scientist at Uber, Sam Swift, the VP of data science at Betterment, and also a former TDI fellow, and many, many more. And if you're interested in seeing those episodes, I really encourage you to also sign up and go to our website to sign up and learn more. Now, before I introduce today's speaker, I want to remind everyone that you can pose questions on YouTube in the chat area on the kind of right-hand side of your screen. We'll monitor those questions and pose them to the speaker at the end of our time here. And you have to be logged into your Google account in order to pose those questions. So without further ado, I'd like to introduce today's speaker. Today, I have the pleasure of speaking with one of the leaders in the data science industry, Julia Silge. I hope I got that right.
You did.
Yay.
All right.
So Julia is a data scientist at Stack Overflow. She has a PhD in astrophysics and worked in academia and ed tech before moving into data science and machine learning. She's also the author of Text Mining in R, and she enjoys making beautiful charts, coding, text mining, NLP, and Jane Austen. So maybe we'll ask her about that. But today she's going to be talking about a topic that we hear a lot about, but maybe is a bit more subtle to implement than one might imagine, PCA. So without further ado, Julia, you want to go?
Yes, excellent. Thank you so much for that introduction, Michael. I'm really glad to be here with you all. Thank you all so much for joining us. So I am going to share my screen here. Excellent. So I am here to talk to you today about principal component analysis, and I am going to be sharing with you about how we can understand principal component analysis deeply using Stack Overflow data. Something that lots of us who spend time coding have some insight into what it means to visit Stack Overflow and have some feelings about that. And so yes, like Michael said, my name is Julia Silge, and I'm a data scientist at Stack Overflow. You can find me here on Twitter or on GitHub. And as a data scientist at Stack Overflow, I work on a lot of different kinds of questions and working with a lot of different kinds of data. And I work on data from questions and answers that are posted on Stack Overflow. I work on data from jobs that are posted on the talent portion of a Stack Overflow. I work on questions related from how can we better match a prospective job to a candidate, to how can we make Stack Overflow more welcoming and more inclusive. The ideas that I'm going to be talking to you all about today to do with principal component analysis are really show how we can understand structure that is in data, how we can understand how we can dig into data that we have and understand what's going on in it. Perhaps unsurprisingly, the first time that I met principal component analysis was not at Stack Overflow. So I want to tell you about the beginning of my story with PCA. And my story with principal component analysis begins as so many good stories do, a long time ago in a galaxy far, far away. So my story with principal component analysis begins with my academic background. So I come from a background in astrophysics, and I studied galaxies. I studied galaxy dynamics and used galaxy spectra. And the first time that I came into contact with principal component analysis, it was in this context. It was in this context of spectra of galaxies, and this was a context that I understood and had deep domain knowledge about. And so it turns out for many kinds of galaxies, if you decompose the spectra into its principal components, the first one, it turns out the components have physical meaning. The first one often comes from the radiation coming from the central supermassive black hole. The next one might come from, say, the young stars. The next one might come from like the older, redder stars. So the first time someone told me about principal component analysis, it was in this context, and I thought, wow, this is great. This makes sense. I understand what's going on. I understand the math that's going on here. Linear algebra is great. This is fantastic. I love it. I'm gonna be able to take this tool with me. I can integrate this tool into my toolbox and move forward. I have some sad news. This is not how everyone feels the first time that they come into contact with principal component analysis. They might have a different experience. They might perhaps be told something like, what we need to do is you need to get the eigenvalue decomposition. You have to take the eigenvectors of the covariance matrix. And I think this is really good, actually, like a really good clear statement. This is from a set of machine learning flashcards created by Chris Albin, who you can find here on Twitter. So this is a very good and clear statement. But oftentimes when students or learners first come across some of these definitions, it is not clear what this means, or how to understand, or how to understand or have some feeling about what does it actually mean to do a principal component analysis, or to do these decompositions from these high dimensional spaces down. So and sometimes you might be like my my co-author on my book, Dave. You might feel like this. You might think, no, I can't. I can't think of this like this. Yes, I like it too. I like it too. And so what we're going to walk through in this webinar is a more hands-on walkthrough of what is principal component analysis, using a example data that a lot of us have some real life experience with. And if you are someone who feels like my co-author Dave, when you have had someone say something like this to you, then this is for you. This is for you. If you are someone who you feel very comfortable with PCA, you feel like, oh no, I've got this down, I understand principal component analysis, then what I would love for you to take away from this webinar is that if you're teaching a new machine learning algorithm, or you're learning something new for yourself, which of course is something that we do all the time as data scientists, it can be very helpful to get a deeper understanding if we put that learning in a context that where we already have some understanding of what's going on. If we can connect a new thing that we're learning back to a domain where we have some understanding, then we can be more successful in using these new machine learning algorithms. So the new, or that context of what we're going to be putting this into, the context that we're going to be putting PCA into to hopefully gain some understanding here is Stack Overflow. So I am a data scientist at Stack Overflow, and at Stack Overflow, we have lots of different sources of data. We have data from people who apply for jobs. We have data around people who are part of our Stack Overflow for Teams product, which are small private instances for companies where they have private and secure Q&A. But the data that we're going to be talking about today is probably what most of you all are think of when you think of Stack Overflow. So picture yourself coding along someday, and oh no, you run into an error. You take that error, you paste it into Google, you search, and some results come up, and maybe the top couple results on Google are links to Stack Overflow, and you click the link to Stack Overflow. And for us on the other side at Stack Overflow, what we see is a visit to a question. So that's the data that we're talking about. We're talking about visits to questions. And hopefully at this stage that actually gave you the answer that you needed, and you can continue on your day, and you can have your solution and move forward. So this data around traffic to questions, visits to questions, means that I spend a lot of time thinking about how technologies are related to each other, about technology relationships. Developers who come to Stack Overflow don't visit tags in random combinations. It's not like developers are just coming and visiting just like a random assortment of questions. Questions on Stack Overflow are tagged with we call them tags actually, but they're tagged with the various technologies. And the any individual developer that comes, either because you're logged in as a user or because there's a cookie, we see that users visit technologies that are related to each other. So we use these kinds of relationships to do a lot of things at Stack Overflow. We use it to make the user experience better, to suggest relevant content to you, and also just to understand at a basic level, to understand how our technologies related to each other. So let's dig into this and show an example. Let's show a concrete example. Let's, in fact, start with me. Let's start with me. So this, let's look at what kind of tags I visit. So I went, in real life, I went into our database, and I found myself, I found my own user ID, and I found what questions do I visit? What of all the questions that I visit, what are the tags that are on them? So I'm largely an R developer. So R is top for me. I visit, that's the top tag that I visit. The next one is ggplot2, my favorite, the love of my data visualization life. And then I was not sure what was going to come after that. I was not really sure what was going to come after those, but to be honest, not a huge surprise here. Next, let's notice these next couple things here. That next one, Git. I'll admit, sometimes, like I bet many of you, I'll admit sometimes I have some problems with Git. Sometimes I get myself into some Git messes. And then you see what's below Git? Regex. Oh gosh, guys, regex. Some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have two problems. Man, it's so true. So true. Yeah, so when I have a problem, a regex problem, I Google it and I find the answer. So this is my own traffic patterns when I see. So let's make some plots of this. Let's see what happens here. So on the x-axis, here we have of all the traffic for a user, what percentage of that traffic goes to our questions, and on the y-axis we have what percentage of that person's traffic goes to regex questions. And that orange dot there that you see there, that's me. So notice that I'm very high up the R direction and that I'm low down the regex direction. Notice that there are so this is a random subsampling of a set of Stack Overflow users. Notice that there's lots of people up. Look at that distribution. Look at the shape of it. There are, first of all, lots of people down by 0. There's lots of people who are not R users. This makes sense, right? Not everyone uses R. Notice that there are not very many people who use all regex. Like regex is nobody's main programming language, right? Like there are many more people whose main programming language is R than whose main programming language is regex. Lots of people use a little regex. There are some people who use a lot of R, but not everyone uses a lot of R. Just kind of like look at how that's distributed and kind of notice it there. Okay, so this is in 2 dimensions. This is just 2 tags. But on Stack Overflow, we have hundreds and hundreds of tags. So the analysis that I'm about to show you takes the top 300 tags on Stack Overflow. So this is just the top, this is for the past year, the top 10. What are the tags that tend to be the highest percent of users' traffic? So which tags tend to dominate individual users? So which tags, for example, will tend to be there are people out there. There are more people out there that tend to have be more Python users than anything else, if that makes sense. Notice that R is up there. R is not like a top 10 programming language. It's more like a top 20 programming language, but people who use R tend to use a lot of R. So that's what this plot is showing, is like how much of a user's traffic tends to be in one language here. So picture that plot I made before, but extended to many dimensions, hundreds of dimensions. So what are we going to do with such a high dimensional space? Well, what we can do is we can transform it to another high dimensional space. And this is exactly what principal component analysis does. Principal component analysis will take the high dimensional space, for example, of Stack Overflow tags, and it will transform it to a new high dimensional space. But it has special characteristics. What are some of these special characteristics? First of all, the axes of the new special high dimensional space they're still orthogonal to each other, and also we make them by taking weighted sums of the old axes. So in this case, we can make the axes of the new high dimensional space by taking weighted sum of Stack Overflow tags. Also, what makes this new space special is that the first principal component is in such a direction that it accounts for the most variance in the data. So we can see this direction is special in that it will account for the most difference in this case in Stack Overflow users. The second principal component is the direction that in this space will account for the second most variation in users, the difference in users. So let's talk about how we might do that. So here is some data, how this data might look. So this is data that has come from our SQL databases. So it's an account ID, a tag, and then this value is a percent of that person's traffic over the past year. So you can see that some of it is kind of high, like there's a user here who visits a lot of PowerShell. A lot of it is kind of low, like you see Git and string here, right? Like people tend to only visit a little bit of get and string. So the data looks like this. This data is tidy. I'm a huge proponent of the power of tidy data. And so it's a really good fit for when you're someone who works a lot with databases. So this data is tidy, and it's great for data cleaning, data visualization. But the next thing I need to do, though, is principal component analysis. So I actually need to get my data from a tidy form into a matrix. So I can do that. This is just a little bit of our code. I don't have that much code in this presentation, but if you'd like to see a little bit of our code, the first line there will take that tidy data and cast it into a sparse matrix. So I end up with a sparse matrix. And then the second line there implements the principal component analysis. The IRLBA package has an implementation of PCA for sparse matrices in R. So it's fast because it's implemented for sparse matrices and performance and worked really well, which is great. And then I'm someone who I always am going to prefer to deal with tidy data. So I'm going to take the output of the IRLBA and then I'm going to convert it. I'm going to tidy the data. So I'm going to tidy it back, get it back into a tidy form there at the end. So once I have, so this is basically all the code it takes to run to do what it is that I'm interested in doing. And then the output, after the output is, if we take a big picture, like a 30,000 foot view, it looks something like this. So this is the first 6 components. So on the x-axis here are Stack Overflow tags. So all 300 or so Stack Overflow tags. And on the y-axis is how much does each tag contribute to that principal component. So this looks quite beautiful, I think. It's not super informative, but you can see like, oh, yes, okay, we see that different tags are contributing at different levels to the different principal components. So just remember, each of these principal components is a new axis in this special high dimensional space. And they are linear, they're weighted sums of the old axes, which are the Stack Overflow tags. So let's zoom in and let's just look at the first one, PC1. And let's not only zoom in, but let's just look at the ones that contribute the most. So let's filter, order, and put the labels back on. And let's look at what we have here. So first, let's look at those ones that are positive. What do we have over there? We have HTML, JavaScript, jQuery, CSS. So these are all front-end web development technologies. Let's look down there at the other end. We've got various kinds of Python, list, dictionary, string, Linux, NumPy. Basically Python. Maybe it's Unix, maybe
scientific Python, because there's NumPy.
Yes, Python with maybe some scientific Python in there. Although the fact that there's like Linux and I would say it's probably probably just Python in general. Probably people who are using Python for sysadmin, DevOps, and probably all together. So what does this mean? This means, remember, this is the first principal component. So what this means is the thing that answers the question, what most distinguishes one Stack Overflow user from the other Stack Overflow user is to what extent are they a front-end designy developer, person who codes, or are they a Python, maybe sysadmin, maybe backend, maybe data person. So that's that's what we find. That's what this result is telling us. So this
front end versus back end.
Yes. Maybe front end versus back end. Maybe front end versus Python sysadmin. Maybe something along those lines. So that's what we're finding here in the first principal component. So I don't know about you, but I'd like to see more. So let's go over here to, so this is a Shiny app that I've made. So this is all built with Shiny and R. And so this is the same component. This is the first component. And we can scroll up through a few and look at them and see what else we find here. So the second principal component is it's less like it's less even. It's less like a one versus another thing, and it's more like a yes, no. It's more like a yes, no question. And what we have here is C#, Visual Studio, Link, ASP.NET. So this is the Microsoft tech stack. So the second principal component is largely, is this developer a Microsoft tech stack developer or not? The third principal component is, again, we've got the Microsoft tech stack over here, and we've got Java, Spring, Maven, Spring Boot. So this is like Java developers versus C#. And we can keep going up here. The fourth principal component is, on one end, Android, iOS, iPhone, Xcode. So on this end, we have mobile developers. On this end, it's SQL. SQL and Linux. So we've got like DBAs, sysadmins, basically on this end. So as we scroll up through here, so here we've got, so this is Linux, Shell, Bash, Unix. So these first couple here are definitely sysadmin Linux, and then we're starting to get some weird combinations. They're starting to look a little bit less coherent, this is just real life. This is what happens as you start to go up higher. The math, this is just what the math happens. We start to see things that still are coherent, but they're starting to get a little weird. The 7 is interesting because you have on one end, Android, everything. On the other side, you've got iOS, iPhone, Swift, Xcode, Objective-C. So this is literally, this is mobile developers, but is it an Android mobile developer or an iOS mobile developer? So that's literally what this principal component is distinguishing between. I don't want to go through. I mean, you see very interesting things through all of these. I think there's for a data audience, this one's kind of interesting. Like we see big data technologies here: Hadoop, big data, Spark, Hive, Scala, MapReduce. So we're seeing here people who visit these kinds of tags are going to be together. Like these are the things that people visit together. So let's make this one here. So this is where we're just looking at what contributes to each principal component, but we can also look at how these components project down into two dimensions. So remember, this is a hundreds of dimensions, high dimensional space, but we can project it down into 2 dimensions. So remember, PC1 is front end development down to Python, backend, sysadmin. And remember, PC4 is big data people. So this is big data people off this way. And you can see where are people distributed in here. So this is big data people who use more Python, right? Like that's what this group is down here. And then people who don't use so much of that stuff. So we can, for example, go back up here. And so this is PC1 and PC2. So you can see here is what % of the variance is explained. Notice these aren't super high numbers, but that's just real life. Like people are different from each other, and we can only explain so much of the variance, even in the top couple principal components. So PC1, remember, is, so this is like front end, back end, and then this is how much does someone use Microsoft. And so so that's how we're getting this shape here, is like Microsoft front end, back end. And of course, someone can use Microsoft and do front end, so that's why we end up with these shapes like this. And as we scroll.
But it's really interesting that this front end, back end split is more prominent for Linux users, apparently, than it is for Microsoft users.
Exactly. And then PC3, remember, was the Java one. And so you end up with all these interesting projections. And so this understanding your data, PC4, I don't even remember what that one was. PC4, was the Android, the mobile in the negative side and SQL on the positive side. So PC4, PC4 is, so this, okay, so that's interesting. So this, so look how this is spread out so big this way and not this way. So that's pretty interesting. That's pretty interesting. So when we do this kind of analysis, like in real life, like for work, like this is very helpful information for product managers, for, like if I can, and especially if I'm able to explain to them, like, what do these things mean, right? Principal components, like, let's understand who our users are and how we can build for them. And also for me as a data science to understand how all this works. So because of the way these principal components, they don't account for a super high amount of variance, these might not be good principal components to use as predictors in a machine learning model, perhaps, but it is very helpful for understanding what our users are like. So I'm going to come back over here to my presentation and talk about one way I've used data like this. So this is back from over a year ago now, but if you remember, Amazon was all the talk was like, where is Amazon going to put their second headquarters? Where is Amazon going to put their second headquarters? And at the time, they had this list of 20 finalist cities. And they said they wanted these certain things about it. And we have data about those 20 finalist cities. And we could, for example, use our data to say which cities are most and least similar to Seattle, where their first headquarters are. And so you could use this, in fact, to say things like, well, if you wanted to go somewhere that's most like where you already are, you could choose, some place like the DC area, or like any of those cities like Northern Virginia, Maryland, DC, or Pittsburgh. Or if you wanted to go somewhere that, for example, had more mobile developers, like we could use an answer. We can use our data to give answers like that. So this is an example of how you can use data like this to answer real life questions. So if you're interested in looking at this more, there's like a whole blog post that I wrote about this, and you can dig into it and see the plots a little bit more.
And it's interesting that they chose Northern Virginia as one of their locations, for those of you who have been following the HQ2 saga.
Which, yes, exactly. So today I focused on traffic data. And that's just one part of the kind of data that I deal with on a regular basis. And other kinds of data that I deal with are data from our Q&A site. So who posts and answers and votes and edits, and how can we use that to understand community health? I also deal with data around jobs. What kind of jobs are more or less attractive, what's in demand right now, and so we can use all of this kind of data to understand things about the technology industry, and also how to build healthy communities and how to support them. And today I talked about principal component analysis, but at Stack Overflow, on the data team, we use a really broad set of tools. Like we are largely generalists. We work with A/B testing. We work with classical hypothesis testing. We use things like logistic regression, regularized regression, Poisson regression. We do things with seasonal decomposition, other kinds of dimensionality reduction. So when I think about like what are the things that have had the most impact, like what are the types of techniques that have had the most impact for our organization, I almost don't even like to think about the techniques, but rather the fact that the people on our team are people who love to learn and people who love to figure out what is the right technique for the kind of question that we want to answer. And with that, I will say thank you to the members of my team, Nick, Kevin, and Jason. And say again, you can find me on Twitter at Julia Silge, and my personal blog. I blog for Stack Overflow some, and then I blog at my personal blog there at Julia Silge, and say thank you so much. So let me stop screen sharing, and we can chat about questions that people have.
Yes. So I think we had one person who wanted to understand how you just decided to use PCA. So maybe one that comes to mind immediately would be something like non-negative matrix factorization. How did you think about that process of how you decided which one you would use?
Yeah. So for this particular application, I use PCA partly as a way to kind of talk about a classic thing that it would be good for us to understand. One, I think a particular like dimensionality reduction, or like where we want to see how things we want to see structure that is in our data. Some things that I think one that has been really helpful to my team lately has been like UMAP. Like it's been something that has been really great for understanding, for example, users in a high dimensional space or jobs in a high dimensional space. Like if we have all these if we have like all these all of this like sort of sparse but high dimensional data, those, if you're looking for something that is fast but has more, that's more recent, has more has some nicer characteristics than actually PCA, I think UMAP is a really great thing to look at.
And just so the audience knows, you're talking about the uniform manifold approximation and projection?
Yes, it's really great.
Okay, very cool. We'll have to check that out. And someone wanted to sort of just take a step back. Can you talk a little bit more about the meaning of the negative and positive components?
Yes.
Yes.
Sure. So it doesn't picture the original high dimensional space. It has the axes are the tags, the technologies, and then in the new space they are these weighted sums of the tags. And in some of them, the way users work, people are being more likely to do one thing makes you less likely to do another thing. Like people who are front end web developers who work on making like the websites that we like make them work with human beings and look nice, like those people are less likely to do things like systems administration or to work on Python and backend. And so that's why they end up with opposite signs. The fact that one is negative and one is positive actually is not physically meaningful. It could actually flip the other way, and it would not be it does not have any like meaning that one is positive and the other is negative. It could flip. The fact they're of opposite sign is meaningful, but the fact that one happens to be positive and the other negative is not meaningful.
Got it. Yep. And as a mathematician, I guess I would say that it's invariant to scaling up to a constant, and that constant could be negative.
Yes.
Yes. So we had a question about careers in data science. How did you make that transition from academia into a sort of data science and ML?
Yeah. I think most people who have the kind of roles I have, and maybe I've had them for 2, 3, 4 years, like to say, oh, I had such a weird path into data science. But I think I really did. I think mine is really weird. Okay, so it's not weird that I have the academic background that I did, right? Like that is excellent training for the work that I do now. I have a PhD in astrophysics. I did a postdoc in physics after that, and taught as a professor for a little while. So that's all great training for doing data science. My actual personal path involved moving from like the research world into a more education oriented role for a while first. Actually, I worked at first I just had like a teaching oriented role, like at like a university teaching role, and then I worked at an ed tech startup for a while. When I was at that ed tech startup, I had like a half content role, like content generation, like for like higher ed physics and astronomy courses, and it was kind of a half technical role, like involving some coding, and it wasn't really my favorite kind of coding. It was actually some of that front end. It was for like interactive homework, and it was actually not my favorite kind of coding. I was like, well, I'm glad to be coding again, but I remember liking like the data analysis and statistical coding, numerical coding. I did better, and I started to see, people from like my cohort making this transition into data science, and I remember hearing about like the jobs they were doing and thinking, wait, that's a job you can have now. And that sounds amazing. That sounds perfect for me. Like when I would think back to my academic career, that's what I liked. Those were among the things that I liked the best about those years that I had in academia. It was spending my time writing code to analyze data. Coming from a background in observational astronomy means I had this background in dealing with real world messy data that in that case was generated by a physical process and then recorded by an instrument that, like there's these processes generating the data that you then analyze, and like having a deep understanding of like how do you understand how to write a reliable pipeline to handle that. And at the time, it was big-ish data for resources we had, so I had a little bit of that kind of experience of understanding like some of the computational tools for dealing with what now seems, it's embarrassing now to say how big it was, but at the time it seemed big. Okay, everyone. No. Anyway, so that's some of the like background. If people now are like wondering like, okay, how actually did you get those jobs? Like how actually did you get those first jobs? What contributed to me getting into some of those, like getting into those transitions and making those jobs. I spent about 6 months updating some of the skills that I had. I had strong like practical data skills, but I needed to update my machine learning skills, because at least from when I was in physics and astronomy, there was not an emphasis on modern machine learning. I think that has changed largely in physics and astronomy. I think there is more emphasis on it now than there was when I was in it, back in grad school. So I needed to update that, like to modern machine learning methods, and then I needed to update to the tooling that people use now. A lot of that practical data skills that I had involved writing in very low level languages, which are not really what data scientists are hired to code in now. Certainly having those abilities to code in those low level languages means that I was not intimidated to learn these other scripting.
I was going to actually ask about that. How did you pick up R? Because I know the astronomy community is very interested, or is a big, or kind of devotees to IDL, right? Is that what you did for grad school?
No, okay. So this is very interesting to me. Yes, astronomy. So when I was in astronomy, there were the people who used either IDL or even IRAF. I'm going to show my age. People are going to be able to guess how old I am. IDL or IRAF, which are, for people who don't know, these are the closed source, proprietary, expensive license equivalents. If you come from a statistics background, it's the equivalent of like SPSS or Stata, like expensive. It involves usually a lot of like clicking. There's GUIs, there were those people, and then there were the people who coded in low-level languages, and those people largely coded in either Fortran or C. And so I was a C person at the that was all those data pipelines that I wrote were all written in C. I also did a little bit of embedded work because I worked on instruments as well. Like I worked on the like the cameras that go on the back of the telescopes. So I worked on, so that involves like what's like IoT type coding now, like embedded devices, and that's obviously just C, right? For the way embedded devices coding is now, like you write C to run little drivers to actually physically move things, like now that I write everything that's just for like a website, it's funny. It's like, yeah, I used to write code that physically moved things. So when it was like, okay, so I had that background, and then it was time to do, then I had like the front end sort of experience, and then I'm going to do, I would like to move into this data science role, and I don't know the right languages. I dabbled in both, in Python and R, and I am very supportive of like, pick the, whatever community is right, and like whatever language is right, and like the Python data community is wonderful, and I have nothing but good things to say about Python as a tool for data. For me, what I think made made R for data science click for me so well is that specifically the tidyverse approach to data analysis and data science is an explicitly like functional programming approach, and that has always been my inclination, and it just clicked. It just clicked for me. So it clicked for me both from a how are the APIs of these functions for data analysis written, and also it clicked for me in terms of what is the characteristics of these communities. The R community is has a lot going for it. And I mean, I'll be honest. Like I had kind of taken a step back from for a number of years from the sort of STEM and tech communities, and gone into these more like education roles. And when I decided, I was like, okay, I'm gonna make this transition back to data science. I'm gonna like learn some of these languages. I literally felt like I was like, okay, going back in, time to get ready. I'm going back in. And my experience, especially in like the R open source community, was so unexpectedly wonderful that it was just like a real shock. And so that's part of it as well. So both the functional
Wonderful.
programming aspect and the characteristic of the community.
Wonderful. And what tool are you sort of most excited about learning now going forward?
Oh, that's a great question. Tool am I most excited about learning?
Technique.
Yes, that's a really good question. So I'm going to say one that I have already started learning, but I'm really excited about putting into greater use. And that is APIs for publishing either data deliverables, model predictions. So like there's so many things like as APIs from R. And I know that they're like, so in Python, there's been support for this for a little bit longer. In R, it's the Plumber package, and
Is it also part of that tidyverse?
It's not explicitly tidyverse. No, it is supported by it is supported by RStudio, so it's connected to some of the similar people, but it's not connected to, if you're someone who's like, tidy data principles aren't for me, like, no, I don't, Plumber APIs would still be extremely useful. And so Plumber APIs are something that have made my real life day-to-day work have just lowered so many barriers, have improved the life of my collaboration life with across my organization in so many ways. One example is the Stack Overflow developer survey, which was published a couple weeks ago. During the process of like that analysis and getting that website built, like I would publish the data deliverable. Like I analyzed the raw data, had aggregated, summarized results. I would publish that data deliverable in an API, like an internal API. And then the developer, like Vinko, my buddy on the developer survey, would take that API and then like build out the site. And so there, like before, so it's like, oh, I can do anything as an API. It turns out, so the ability to, for example, have models exist as APIs, and many other things. This is I think having like realizing R is a real programming language and we should treat it like one are some of the things that like just make my life so much easier, and and also upping the sort of software engineering savvy of like our like across my own work and like how we deal with data. So I'm going to say that.
Cool. Wonderful. Well, thank you so much for taking the time, Julie. I really appreciate it. And I also like to thank the audience for joining us. I hope you enjoyed this latest installment of DS30. If you are interested in our free data science fellowship for PhDs and master's students, you should apply online at thedataincubator.com. And if you're looking at online courses for professionals or train, feel free to go to www.thedataincubator.com. All right. Thank you, everyone.
Thank you all so much for coming.